Okay. Good afternoon, everyone, and thanks for joining our Tales in Tech live webinar. I'm Simon Evans. I'm a director at Burn Sheehan, and I head up our software engineering function. Over the years, we've run dozens of events, but it's only been recently with the restrictions in place that we've started running webinars. And I have to say, the reaction in our community has been overwhelmingly positive. We initially started with topics covering sort of the changes and the challenges that businesses are facing around distributed and remote teams. We also have a diversity and inclusion webinar coming up in the next couple of weeks, focusing on attracting, recruiting and onboarding a diverse workforce. However, we haven't lost sight of the fact that we're all techies at heart, and so we'll be hosting many more Tales in Tech in the coming weeks and months. To kick off the Tales in Tech series though, I'm delighted to introduce Michele Sollecito, Head of Engineering, Architecture and Delivery at Football Index, who will be talking with you today about reactive Kafka processing with Kotlin. He's happy to answer any questions you might have, so please use the available Q&A function. Michele, over to you.
Thanks, Simon, and hi, everyone. While I share my screen in a second, welcome and thanks for the opportunity. So, do you see my screen? I think it should be fine. Simon, can you see it just for me to?
Yes, I can. Yeah, that's working well.
All right, perfect. So, welcome again. I'm Michele Sollecito, the Head of Engineering, Architecture and Delivery here at Index Labs. What is Index Labs? You might be asking yourself. Index Labs is basically like the company behind Football Index, which is our main product. And Football Index is essentially a betting platform, and we launched that in October 2015, so it's not exactly yesterday. And as a product, it basically allows users to buy and sell shares of football players, which are not really shares, they're more like fixed odds bets, because we are regulated by the Gambling Commission rather than the FCA. And the entire point of the game is that you buy and sell these shares of football players, and based on how they're doing on the field and on social media, we pay out dividends during the year, right? So how is it going? Well, it's going fairly well. So these stats are basically like during the initial time of Corona. Now things are a little bit better, but fluid. So I'm waiting before giving out better stats, but at that time, we had about 155,000 users, of which more or less a third were active monthly. And this is just the UK, because we are primarily a UK company, right? The portfolios for these users, they basically range from as little as £10 to up to £2 million. So this is not just like fantasy football, but people actually took us fairly seriously, right? And in 2019, we basically traded for about 650 millions, and we pay a little bit more than 8 millions in dividends. So what are we talking about today? Today we're talking about a topic which keeps coming up in more and more companies these days, right? The more they use microservices and so on. And it's basically like a comparison between two different architectural patterns for microservices, one of which is called orchestration and the other one's called choreography. Now, the reason why we talk about this in this kind of event is because, using orchestration and HTTP requests with microservices can result in essentially this mess you can see on the screen. And, eventually you got many microservices, each with their own database, if you're lucky. If not, it's even worse. And they basically talk to each other a bit of an ad hoc mechanism with different protocols, different strategies when it comes to retries and so on. And the result can have quite a few problems. Like in particular, if we're talking about a chain of synchronous calls, well, the availability of these chains, assuming that there are n microservices involved, will basically be the product of all the availabilities of those services. And if the availabilities are less than one, like always, this is a negative thing. And the other big problem is throughput, right? So if you need to calculate how many requests per second can your overall platform support, well, this will be the minimum given a chain call of microservices of their own throughput, right? So it doesn't matter if your first service can absorb, I don't know, 200 requests per second. because if your second service in the chain can only absorb 50, that's what you can do without having problems. Right? And you also tend to need distributed transactions, or you need to be very careful about what you do with idempotency and retries, because otherwise you end up having data inconsistencies, and everything is like push based, so there's no back pressure. If you underdimension your system, things will be killed by latency and by literally traffic, right? And also HTTP requests are transient, so they're not replayable, and as such, it's very hard to provide an audit trail or things that are very, enjoyable in general. Now, choreography, on the other hand, is really simplified when it comes to flows, right? And in particular, the way this tends to work most of the times is that, an initial service, which is typically a REST endpoint these days or something similar, will produce an event on a commit log. And, while we're talking about Kafka, this is one of the things that Kafka does very well. And after that, it will terminate the synchronous part of the request. And after that, what's happening is that there's an asynchronous and eventually consistent pipeline of processors will basically enrich these events. And and the next processor typically consumes the event produced by previous ones. And these events will eventually end up into some databases that can act as materialized views for other endpoints which serve GET requests, and this is called CQRS as a pattern, and can also result in push notifications that are sent from the server to the client, right? Now, this has a lot of benefits compared to orchestration. And, in particular, the big benefit is that the availability is the availability of Kafka itself. As long as Kafka is available and your, REST endpoints are available, you can still accept traffic, even in something downstream is not really working. And in particular, Kafka has been built for availability, so it can be clustered and scales really well. On top of that, the maximum request per second you can serve is once again the throughput of Kafka itself in terms of ingestion, because it essentially behaves like a queue. And also, everything is pull-based, it's back pressure, the excessive load is enqueued, so there is not much need for redundancy, and it's much easier to avoid errors that can really impact the end users. Typically, if there's a problem, it results in latency rather than in unavailability. Now, an additional set of benefits, and this is a really big one, is that with this architecture, everything is durable, it's replayable, it's very easy to provide an audit trail because you got the entire sequence of events, which you can use to prove, why you did certain things. If you're regulated, this is like a very good benefit that in general is quite hard to achieve. And if you generate some client-side IDs, you can use those for the duplication to achieve idempotency. So how do we get from Kafka, orchestration, and choreography to Kotlin? Well, because basically Kafka is amazing, and it comes with different APIs that you can use to basically produce and consume events, right? Now, starting from the lowest possible level, there is the native consumer and producer Kafka API, which works. It's kind of okay for basic message passing when there are no external interactions. But first of all, it's a very low-level API, so there's a lot to configure, lots to do, a lot of pitfalls. You need to basically take care of doing things properly. And it's callback-based, so there are blocking semantics, which means you cannot really wait for an asynchronous operation inside a callback. It doesn't work that well, right? and as such, it's not the most, advisable mechanism where message processing requires external interactions. Like as an example, if for each Kafka event, you need to read something from a database and then reach that event with that information, this model is ill-suited, right? Now, there's another library which was built to address these concerns and some other problems, which is called Kafka Streams, which once again is native, so it's provided by Kafka as part of the Kafka project itself. And it comes with very sensible defaults. It's easy to use. There are few pitfalls, which is great, you know. And it comes also with streaming semantics. So you can basically do things like, hey, for this stream of events, you know, map with this function, and then the result output that on another topic. Very nice things, you know, materialized views, window aggregations, things that in general not that easy and are made really easy by this library. On the downsides, there's mostly two. So one is that despite being about reactive streams, Kafka streams has blocking semantics for the intermediate transformations, which basically means that you can have a reactive stream of events, but then if you need to map a function on them, then that function will have to have blocking semantics, which is probably some serious design issue, because once again, it means that if you need to enrich that while talking with the database, you know, your threading model will suffer from it. And the other big problem is that it is exposed with Kafka-specific streaming API. So it uses some types to model reactive streams that are specific for Kafka. So this might or might not be a problem, but in general is not the best. So there's another library which was built by the authors of Project Reactor, which is called Reactor Kafka. Now, this basically is strongly inspired by Kafka streams, and it solves quite a few problems. So it's a very high level API. So once again, sensible defaults, very easy to use and not many pitfalls. It has end-to-end non-blocking back pressure. So even intermediate functions have reactive semantics, which means you have really good resource utilization, and you know, you can use non-blocking IO and so on. And it uses a general purpose streaming API, in particular Project Reactor streaming API, which is general purpose. And the downside compared to Kafka streams is that it doesn't provide support out of the box for materialized views and window aggregations, which are really powerful. And unfortunately, they're not there, right? So how about Kotlin? Well, when it comes, I mean, Reactor Kafka was created for the JVM, so it works with any JVM language, right? And if you use Java, there's not much you can do, right? You can use Project Reactor for your functional types and interfaces and whatnot, and basically like use intermediate transformations using Project Reactor itself. Now, the really good thing about Kotlin is that it comes with its own reactive streams library, and these are called coroutines and flows. And essentially what you can do is you can use Reactor Kafka itself as a library, but basically bridge that and transform a flux of events in Project Reactor semantics into a flow of events in Kotlin flows semantics. And this basically gives you quite a bit of benefits. I mean, the first benefit is that the API is really cleaner, because basically the language itself understands suspending functions. So you don't need to have, as an example, a map and a flat map. You can use just map, whether it's suspended or not. And also, Kotlin has structured concurrency. So it basically means that, typically, if you use Reactor Kafka, you have to subscribe, and do whatever you need to do, and then make sure you close the subscription. Otherwise, you end up potentially creating resource leaks and things like that, right? Now with Kotlin, given that you basically append this processing underneath a coroutine context, this is structured concurrency. So it means that at the end of the application lifecycle, it will be closed automatically, and you don't have to worry about these things too much, right? Another advantage is that Kotlin flows are at least twice as efficient when it comes comparing them to Project Reactor. So everything is faster and requires less memory. And it's almost perfect. And I'm going to show you some code in a bit. But basically, the last problem, we'll talk about it in maybe 10 minutes, is that it still doesn't support materialized views and window aggregation. So I'm going to talk to you about how to actually implement these things. So let's have a look at some code, right? So I'm going to step out of here. So bear with me for a second. I'm going to stop my screen share. I'm going to share another window. which is here. Okay, so hope you guys see it. Can you read the code? Anyone? Can anyone confirm any chance?
Yeah, we can see that.
All right, cool. So I got like my Kafka processing test, which is just a demonstration. You know, what I do is I use test containers to basically like initialize a Kafka standalone environment. And after the test, I tear it down. And then I prepare a string serializer and a string deserializer, which are able to tell Kafka, you know, how to map my key value pairs. And typically what I do, and this is the beauty of using Reactor Kafka with Kotlin, is that the code stays really functional, it plays really well with extension function, and it's relatively straightforward to understand. So here I do a bit of preparation. I have a topic called test Kafka processing messages. I mean, the name is just whatever. I get a sender, so I'm able to create myself a sender that I will use to publish messages, and I create a receiver. So the same kind of thing. And now I create some records. So in this case, I just have key value pairs. So basically I have, you know, I map 1 as a number to hi, and 2 to hello, and 3 to hola. Fair enough. And I create myself a mutable map to store these messages as I receive them to test that, you know, my logic is correct. And then what I'm going to do is I'm going to produce these records, log each of them that has been produced, on completion, log that I finish producing them, and then I'm going to subscribe. And then what I'm going to do, what's happening here is that when I call subscribe, this will not wait until all this thing is finished, but it will basically proceed because all the stuff is asynchronous, right? So here what I'm doing is I got a flow of events out from the receiver, and on each I log it, I add it to the received messages, and I also acknowledge the offset from the event in Kafka. And after, you know, receiving 3 records, I will cancel my subscription because it makes no sense anymore. And then after that, I will log that I finished receiving, right? And then here, what I do is I will say, hey, waiting for completion, await both produce and receive to be finished, and then say that you finished. And then after that, I basically assert that I receive all the events I expect. So I'm gonna run this. So hopefully, fingers crossed, nothing terrible happens at this moment. Famous last words. Now let's see. Okay, that actually worked. I'm happy. Right, so let me zoom a little bit. Let's see what happens here, right? So as I was saying, the first thing that actually gets printed is this line here, processing waiting for completion, right? And then you can see that the sender actually does its job. And you know, you can see that I'm sending offset 0, fair enough. I'm sending, and you know, I'm sending offset 1 and offset 2. And then it says finished processing events from a sender point of view. Now the sender is closed. The receiver starts, so I received the first one, fair enough. And here the value is high, the second one is hello, and the third is hola. Then I finish processing the events and everything finishes, right? So why are all the events sent before they are all received, right? I mean, this would be a legit question. Well, typically because there's a bit of latency and, you know, the producer is really fast. So what happens is by the time I start producing, the receiver, there's a race condition, so it's still not subscribed, which basically means that, you know, I send everything because once again, Kafka is really fast to ingest, and then the receiver comes up and it consumes them, right? So what I can do to show an alternative is I can say, okay, on each of these records that I'm sending, introduce an arbitrary delay of, I don't know, 500 milliseconds, whatever, right? And then if I run this thing again, once again, hopefully, okay, now you can see that they interleave, right? So essentially what happens here is I go processing, waiting for completion, then the sender sends the first event, the receiver receives the first event when the value is high, and then it's acknowledged, and it happens again for the other two. Well, actually, in this case, it didn't happen for the other two. This is kind of cool. It shows you that it's actually asynchronous. So what happened in these other cases is that actually the sender was quicker and just sent the other two, and the receiver received the other two. So basically, the order was send one, process one, and then send the other two and process the other two. Fair enough. Just to show you that everything is asynchronous. Now let's go back to the slides, because we still need to talk about, how do we implement materialized views. So let me stop the screen sharing again, and I'm gonna share my presentation again. Okay, let's play it again. Okay, so what about state, right? It's all about state. Now, the problem is these in-memory processors are really fast, really convenient, really easy to understand. But, well, if they crash, how am I going to rehydrate my, in-memory state? So what is an in-memory state, just in case? So imagine that, I don't know, I'm a balance service, right? So for each transaction, when someone requires to buy something, I need to actually keep track of their balance, validate if they have enough balance, and if they do, reduce the balance and produce an event saying that they paid for it, right? Now, typically, you keep this balance in memory, and you can basically do this calculation while, producing the new value of this balance in memory, and then you publish an event saying that something happened. Now, this is great because it's blazing fast and you can process thousands of events per second very easily. On the other end, what happens if you crash? So it is true that all events are in Kafka. So theoretically, you can reconsume everything that has ever happened for that user, including all deposits, all transactions, all withdrawals, and everything else. And you will be able to reconstruct this in-memory state. But if you think about the fact that some systems might be, I don't know, several years old, and you might have to process thousands of transactions per second, as fast as Kafka is, it's not that fast. So in general, it's not a great idea to having to reconsume the entire history when you crash. And we said that Reactor Kafka does not support these durable state snapshots. So one thing we can do is we can use this pattern, which is actually pretty cool. And is essentially write ahead, which is used by databases themselves. And what happens is you can have a disk-based state snapshot in write ahead configuration. Now, typically, a great technology does that you can use to implement this, even if it's not the only one, is this technology called Lightning Map database, right? Memory map database. So how can you use that? So there is basically, this is a kind of the workflow. So the main idea is you would compute the result from the memory state, like usually. So we said, if you're a balance service, imagine that the current balance in memory is, I don't know, 100 pounds. Somebody wants to spend 20 pounds for a transaction. Now that transaction is acknowledged by the balance service, and the new in-memory balance is now, 80. Now, what happens is, you update the memory state, and then you publish this event saying that a transaction was acknowledged and it costed 20 pounds or dollars, whatever. Now, how do you make sure that you keep track of state in a durable fashion? Well, eventually what happens is that you have a consumer which consumes the output events from the balance service, and it will see that a transaction worth 20 pounds was acknowledged. So what he will do is he will go in the database and say, okay, now at offset 123, the balance was 100. So now at offset 124, the new balance will be 100 minus 20 from this transaction event. So basically you will store this state itself against the offset coming from the Kafka topic. Now, if you do that, what can happen, and this is called write behind, because it's typically, it's called write ahead, but it's called read behind, because this durable state will be behind, so that the memory representation will be more up to date compared to the durable one, right? So what happens when you crash? Well, what happens when you crash is that when you restart the service, you will read the state and the offset from the disk-based durable one, right? So when a service starts, you talk to Kafka, say, hey, which, what is my latest durable snapshot from disk? Okay, is offset 1 to 4, and the balance was 80. Okay, nice. So you go to Kafka and you reconsume all the events starting from the disk-based offset, right? So as an example, while you crash, there might have been some other events. And what happened is that, I don't know, maybe now the offset in Kafka is 135. So what happens is you start by 124, which is the latest durable one you acknowledged, and then you reconsume all the events from 124 to 135, and you reapply that to your in-memory state, which you initialize to the disk-based value, right? And so after you've done that, you resume with an up-to-date in-memory state. Well, it's actually a very quick mechanism, right? So with that said, I mean, I thank you very much for the time and the opportunity again, and you can see my contacts on the screen. And with that, we can probably open the Q&A session. So I'll stop the screen sharing. So if you have any questions, okay, there is a Q&A. All right, let's see. I assume next app web services are running on cloud, right? Just wondering what do you think about managed solution come from cloud? Okay, so I read it out loud, right? So the question is this. I assume that Index Labs web services are running on the cloud, right? Just wondering, what do you think about managed solutions like Confluent Cloud, AWS MSK, or roll your own Kafka cluster using Kubernetes or EKS, right? And so basically, the thing is this, talking about this question, I mean, obviously running Kafka is not a joke. And there's literally departments that do that and commercially. And Index Labs is not a huge company because we don't want it to be, which basically means that we were fairly quick to exclude the possibility of running our own Kafka cluster. So we did some analysis, between basically AWS MSK, which is managed Kafka run by AWS, and we compared that with Confluent Cloud. And we also compared that with something else, which is called Kafkask.io, which is probably the one we end up using. And the reason why is because Kafkask.io is actually a managed Apache Pulsar, which is a binary compatible product with Kafka, which has better support for partition rebalancing and cold storage options for older events. So while we say Kafka, there are some other products which are binary compatible with Kafka, but are based on some recently open source technology by Twitter, which gives them some additional benefits on top, right? So to answer your question, we basically consider quite a few options, all managed options, and realistically, we'll probably end up using Kafkask.io. So there's another question. Have you had any compatibility problems with Reactor, working with other libraries, testing frameworks, and so on? No, not really. I mean, Project Reactor is immensely supported. Like as an example, it's basically used by Spring Framework itself these days, and Spring Boot has this option called Web Flux, where basically like it allows you to use a reactive web server, basically giving you semantics that are based on Project Reactor. And essentially you got this thing where, I don't know, your request body would be a mono, which is a Reactor monad of the actual request body, and you would return a mono or a flux as part of a Spring Boot controller. So it's actually very popular. It's very easy to integrate, and I use it in Java before extensively, and transforming that into Kotlin type is just easier. But no, it's very, very easy. The only problem with reactive types, and that's also another big deal with why Kotlin coroutines are easier, is because debugging project Reactor, chains is not necessarily the most straightforward thing. There are some agents which make the stack traces a little bit more accessible, but like it's much better in Kotlin anyway. Right.
Any other questions out there?
I think that there were some sent by email, but I don't know if we can copy paste them in the chat.
Yeah, bear with me. Becca?
All right, cool. So we are retrieving those two questions.
Yeah. Okay. Yeah, I don't think if there's any other questions, speak now.
Oh, that's one. Cool. Can you use Kafka in a transactional way? It's an interesting question. So there are two things that come to mind, right? So first of all, when it comes to transactional, what it means is, it can mean really two things. Whether you can do some Kafka operations like producing an event in the same transaction. Okay. So you mean like within like a database transaction or something. All right. So, Kafka itself, when it comes to events, it supports transactions like you can consume and acknowledge multiple events or fail and so on. But on the other end, the thing is, when it comes to database transactions, not really, but what you can do is you can use this pattern called the outbox pattern. So as an example, imagine that, I don't know, for me, it's absolutely critical to ensure that, I don't know, the username of a user record is unique, right? And I don't want for this thing to fail farther down the line. I want to validate that immediately as part of the REST service. Otherwise, I want a failure. Well, typically what happens is you cannot use a transaction to, check this thing in the database, store it if it's not there, and also publish something on Kafka because you can fail in between. But what you can do is you can basically write this thing transaction in the database, and then using the outbox pattern, you can consume the bin log eventually and map that to Kafka. So that basically, even if there is no way of doing it transactionally, it will be eventually consistent. I hope that answers the question. Cool. All right, so there's another question in the chat. So in your view, how routines compare with solutions like Reactor Core in terms of debugging and learning curve? So this is one. Well, as I was saying before, I mean, I think Kotlin solution is superior for both. So for debugging is much, much easier because basically the language itself understands the suspending semantics. So basically the support from the debugger is much better. And in terms of learning curve, it might actually be easier as well because there's a lot less operators you need to know. And the reason why is because you don't have all the duplicates, So typically with these reactive libraries, if I have a map function, you can either map with a function that given, say, a string returns an integer, or you can map with a function with reactive semantics, which given a string returns a mono of a string, which is basically the monad applied again. And so typically there's a need for map and flat map and, and filter when and multiple semantics. While with Kotlin flows, it doesn't really happen because you can suspend, which basically means that it's up to you whether you do it or not. So there's another question in the chat, and then there are two more in Q&A. So one says, are you using Kafka streams to do window-based processing? Is having Kafka group records and present a set of records to up? So that's a good point. We are thinking about doing window-based processing, and this can be done by using other technologies. So as I was saying, we don't plan to use Kafka streams because while their support for window-based processing is excellent, they do not support reactive intermediate operators, which for us is even more of a need. But we'll definitely basically use something ad hoc to achieve window-based processing, right? And in particular, no, we don't present a set of records to the application, but we still use it as event sourcing to an extent, because basically what we do instead is we derive materialized views from this set of records. Right, there's another two questions. Oh no, okay, that's fine. That's been done. It was the same question, just thanks. All right. So any more questions?
Okay. Okay then. Well, bear with me. Okay, thank you very much, Michele. That was extremely informative, very entertaining, and way over my head. Definitely, thank you very much, everyone, for attending. I hope you did enjoy it. The video of this and all our other webinars are available on the Bernd Sheehan website and our YouTube page. If you have any topics that you would particularly be interested to hear about, or indeed would like to present, we'd be very keen to hear from you. So please get in touch with either myself or Becca, our community manager. We're always keen to hear from our community to make sure we're providing content that is truly valuable to you guys. So that's it. Thanks again, Michele, and have a great evening, everyone.
Thanks, everyone. Have a great evening.